Welcome to an overview of manufacturing methods. Today's lecture will be talking about material properties and product attributes. Within that context, we'll be talking about the nature of materials, mechanical properties of materials, and physical properties of materials. So let's first tackle the nature of materials. The importance of materials in manufacturing is the follow. Manufacturing is a transformation process. It is the material that is being transformed. As a consequence, the behavior of these materials becomes quite important. And it is the behavior of the material that, when it's subjected to forces, temperatures, or other parameters of the process, that then determines the successful operation of that process. Therefore, understanding the nature of the materials is quite important. So, when we look at the micro scale level, the atomistic scale, the bonding between atoms and molecules matter. Atoms are held together in molecules by various types of bonds. One type of bond is called primary bonds, and they're generally associated with the formation of molecules. You may have heard that. Secondary bonds generally are associated with attraction between molecules. Two different kinds of bonds. One is talking about the formation of molecules. The second one is talking about the attraction between molecules. Therefore, primary bonds are much stronger than secondary bonds, and they'll become important as we continue through these topics. When you look at primary bonds, they are characterized by strong atom to atom attractions, and they involve the exchange of valence electrons. There's three forms of this. One is called ionic, covalent, and metallic. Those are the three kinds that are primary bonds. So with secondary bonds, whereas primary bonds involve atom to atom attractive forces, secondary bonds is looking at the attraction forces between molecules. And the intermolecular attraction that we're talking about here has a name called van der Waals. You're not transferring or sharing electrons in this case. The bonds are weaker than primary bonds. And there's three types, forms of van der Waals forces. This first one is called the London forces. The second one is called the dipole forces. And the third one is called hydrogen bonding. And so we continue then on here. The microscopic structure of the matter matters. Atoms and molecules are the building blocks of more microscopic structure of matter. When the materials solidify from the molten state, which is usually how you start, they tend to close ranks and they pack tightly. And they arrange themselves into one of the following structures, either crystalline or non crystalline. And we'll talk about that a little bit later. But again, the arrangement matters, and that drives whether the structure is crystalline or non crystalline. And we'll talk about that more as well. In a crystalline structure, when I look at that, the crystalline structure is a crystal structure where the pattern is regular and is repeating and is denser. In a crystalline structure, you have a structure in which the atoms are located at regularly and recurring positions in three dimensions. You can take a unit cell, and that basic geometry grouping of the atoms can be repeated. The pattern may be replicated millions of times within a given crystal, and the characteristic structure of virtually all metals, as many ceramics and some polymers, exhibit this behavior. So now, if I look at crystalline structures, there will be sometimes imperfections in these crystals. The imperfections usually arise from the inability of solidifying the material to continue replication of that unit cell. And so that causes these grain boundaries in the metals where this interruption occurs. The imperfection can also be introduced purposefully. You could do that on purpose by adding alloying ingredient metal. You can cause these grain boundaries. There's three types of defects when you're looking at imperfection in crystals. So again, a perfect crystal looks like this, arranged perfectly, but then imperfection can arise, and these ground boundaries will occur when there's the inability to solidify material or introduced purposefully. The three types, the defects you may see is point defects, line defects, also as an example of that will be dislocation, surface defects, which is a grain boundary. So continue on, we will compare elastic strain versus plastic strain. So recall the elastic strain, a situation where if I load up a material, that material will deform, and then when I remove the load, it'll return back fully to the original deformation or initial shape. In this case, all the straining that was occurring was elastic because all the deformation was recovered back to normal. With plastic strain, you do have some amount of residual strain that occurs, and that needs to be considered as well. So when a crystal experiences a gradually increasing stress, it will first deform elastically. That's really what happens. So as you increase the stress, it will deform elastically, meaning when I remove the load, it can return back quite easily. So A here is your original crystal structure. B is an elastic deformation that has no permanent deformation change in positions of atoms. So when I apply the load and I remove it, it goes back to A. So that's B. And then C, if the stress is higher than the forces that hold atoms in their lattice positions, like here, a permanent shape can occur. And what will cause a permanent shape typically is called a plastic deformation or slip that occurs. And here I depict a slip plane. In this case, the atoms are forced to find new homes. I remove the load, and there will be some amount of permanent deformation that occurs. The effect of dislocation strains is illustrated here. So in the series or this series of diagrams, the movement of the dislocations allows deformation to occur under lower stress than in a perfect lattice. So that can occur if you have dislocations, which is an imperfection of a crystal. You could have lower stress required to cause a deformation to occur. So here, what you see is a dislocation, and as a shear stress is applied, that dislocation can move, and you could then eventually cause a slip plane much easier due to that imperfection because there's an atom missing there, and that can make it easier then to cause an issue. So that dislocations in a lattice structure can have an effect. Lower stress required to cause is a slip or plastic strain, and that will occur at lower stress compared to perfect lattice where you have a perfect arrangement with no defects. The slip on a macroscopic scale, the slip occurs many times over throughout the metal when subjected to a deforming load. So that causes its macroscopic behavior to exhibit a particular response in the stress strain curve of the material. The stress strain curve of the material is a material behavior and response of a particular metal or material, and we'll talk about that coming very soon. Dislocations can be a good news, bad news situation. It's good news in manufacturing because you can then form that metal much easier than if there was no dislocation. So, for example, here in this case, it will be easier to deform this structure for the purposes of manufacturing than a perfect lattice like this where there's no dislocations. And so dislocation can be good news in that case because I can deform it for the purposes of manufacturing. It is, however, bad in the design because if you have dislocation, then the metal will not be as strong as we would like to have it. So now let's examine a polycrystalline nature of metals. In this case, it's a block of metal that may contain millions of individual crystals called grains. And so those individual crystals that we call in grains is called polycrystalline because each grain can have its own unique lattice orientation, but collectively the grains are randomly oriented in the block. So again, here you have a regular pattern, and another imperfection can be a grain boundary, right? That we discussed earlier, where the regular structure of the lattice and the atoms is not preserved. Rather, now you have grains that could have within those grains you could have a regularly patterned atom, but those may be oriented differently from adjacent grains. Here's an example of what I'm talking about. So here you have one grain, an adjacent grain, and another adjacent grain, and another adjacent grain. In all these three cases here, each of these crystals may have a perfectly arranged lattice, but you can see that at the boundaries there's an interruption, right? And that's a potential weakness. Here's a 400 microns larger than usual grains that allows you to see a little better what is going on. And you can see extremely large grains even at large scales in a tube pole that supports a traffic light. So what about grains and grain boundaries in metals, right? How do polycrystalline structures form? Is really as the block of the metal cools from the molten state, it will begin to solidify. And so individual crystals may nucleate at random positions and orientations at different times. And so these crystals can grow, could interfere with each other, forming at the interface a surface defect, which we call grain boundaries. And these grain boundaries are transition zones, which are very thin, only a few atoms thin. So really, what is going on here is the nucleation of these individual crystals at random orientations, and that cooling process is occurring non-uniformly. So some crystals will grow faster than others, and that force fight from location to location is really what interferes in these local regions that then form these surface defects that we call grain boundaries. And so here you can see the nuclei of the crystallization in the liquid form. As you freeze and you continue to a solid, you can start to see the formation of these local crystals and then the grain boundary being formed. Here you can see the crystals, you can see certain arrangements compared to others. So what about non-crystalline structure, which we call amorphous structures? Many materials are non-crystalline. You have water and air, which have non-crystalline structures. A metal loses its crystalline structure when it's melted, so it will behave more as a non-crystalline structure. Important engineering materials do have these non-crystalline forms. So glass, many plastics, and rubber have this form. And for non-crystalline structure, you're going to have a less tightly packed and random atoms involved. What are some of the features of non-crystalline structures from crystalline materials? So there's no range order in molecular structure. There's differences in melting and thermal expansion characteristics. The characteristics change in volume for pure metal compared to the same volumetric changes in glass. So there will be changes in these materials. Now, let's examine this diagram here, which is showing the volume unit weight in the y-axis. In the x-axis is the temperature. And here you see two parameters. One is called the glass transition temperature. The next one is called the melting temperature. So what we see here is that a crystalline structure following this line here, which has lower volume per unit weight. So everything's more compact because everything's arranged and tightly packed. Here, this crystalline structure, when it reaches the melting point, will start through the heat of diffusion become a liquid. Then you have a amorphous structure here, which, as we said, is a non-crystalline structure, and that's this line here. And when the glass transition temperature occurs, it continues to change its behavior, and it will become a super cool liquid, and then a liquid. So this amorphous structure, because it's not as tightly packed as a crystalline structure, is going to have a volume ratio to unit weight that's greater than if you had a crystalline structure. I'll let you think about that and kind of pause and have you think about that. So with that, we conclude our topic on the nature of materials, and we'll move on then to the mechanical properties of materials. And I hope you enjoyed the topic, and we will move forward now. Thank you so much for your attention.